So in this video, we're going to talk about the periodic table and patterns in the periodic table. So the periodic table was constructed in order to show the patterns that are observed in the chemical properties of different elements. The way that we have elements grouped in the periodic table now, elements that are in the same column have very similar properties. But it took us a while to get to the periodic table that we currently have. Going back a little bit in history, Dobereiner attempted to group the elements to show elements that have similar properties, but he grouped his model in triads, which is groups of 3. So we start with groups of 3 elements, but that didn't really work very well. So later on, John Newland suggested that the elements should be grouped in octaves. Well, if you go through and count up on the columns of the periodic table, none of them are octaves. And none of them are triads either. And in fact, different columns actually have different numbers of elements. So grouping them by a certain number of elements doesn't really work for either of these models. So later on, Meyer and Mendeleev is the one who's more well known for this. Mendeleev grouped the periodic table by putting elements into groups and by their property. He did it by their properties. So he emphasized the use of putting these elements into groups based on their properties, and by doing that, he was actually able to predict the existence of elements that we didn't know existed yet. And he was also able to use this table to correct some of the values of atomic masses. So this is Mendeleev's early periodic table. So you can see it looks quite different from the one that we currently have. But it was a start. We at least have elements in some similar orders to what we have now. And eventually all these elements got filled in, and we got the modern periodic table that we have. So the periodic table that we currently have is useful for a lot of reasons. One good thing about it is that, as we've mentioned, elements that are in the same group have the same trends. We also can use the order of elements to predict certain trends about elements. So the 3 particular trends that we're going to talk about in this chapter are atomic radius, ionization energy, and electron affinity. So we'll start with atomic radius. Atomic radius is half of the distance between identical nuclear centers. So for example, if we take something like Cl2 and we take the distance between the 2 radii and we measure that bond length, and then we divide that bond length in half. Half of that bond length is the atomic radius. So we're going to talk about how atomic radius increases and decreases. I'm going to explain it the way your textbook typically explains it first, because there is one point that we need to make. And then I'm going to show you an easier way to remember the trends. So atomic radii increases going down a column. So that probably makes sense. As you go down a column, the atomic number increases, which means we increase the size of the nucleus, we increase the number of electrons around the nucleus. Electrons are negative particles, so they're going to repel each other. So as we put more electrons around the nucleus, then we're going to have more electron repulsion, which means that that electron cloud is going to be spread out. so we're going to have a larger atomic radius. However, as we go across a row, we actually decrease the atomic radius. So that might sound opposite to what you would think it would be. But the reason for that is that as we go across a row, we increase the effective nuclear charge. So there are formal definitions, and there's actually formulas to calculate effective nuclear charge. But the key point about nuclear charge is that it has to do with the pull of the nucleus on the electrons around the nucleus. So we're not going to get into the formal definitions and the formula, but the gist of it is that how strongly the nucleus is pulling on the electrons, specifically the protons in the nucleus are pulling on the electrons. So as we go across a row, we increase that effective nuclear charge, which means we increase the attraction for the valence electron. So those get pulled in more closely to the nucleus, which means that we have a decreased atomic size. Now, the easier way to remember this is to remember everything in the direction that it increases. So you can remember whichever way works for you. The way that I like to do it is remember the direction everything is increasing. And once we get through all these trends, I will show you why that way is helpful. So if you think about increasing, we increase as we go down the periodic table, and we increase as we go right to the left. So that means that we have the largest elements, or the largest atomic radius, on the bottom left of the periodic table, and the smallest on the top right. Now, when we have ions, that's going to affect our atomic radius. So cations, remember, those are our positive particles. Those are the ones that have lost their electrons. So if we lose electrons, the nucleus is going to have a greater attraction for those remaining electrons. So cations of mean group elements are actually much smaller than their parent atoms. Anions, there are negative particles. They've gained electrons, so they are much larger than their parent atoms. So the next trend we're going to talk about is ionization energy. Ionization energy is the amount of energy needed to remove 1 mole of electrons from 1 mole of atoms in their ground state. So the key point here is that it's not about 1 electron from 1 atom, but ionization energy is measured based on moles. It's measured in kilojoules per mole. So the energy needed to remove 1 mole of electrons from 1 mole of atoms. So in other words, we're talking about how easily a mole of atoms gives up its electrons. As we try to take away more electrons, the ionization energy increases. So we measure this 1 mole at a time. For example, if we look at magnesium, when we remove the first electron, the ionization energy is 738 kilojoules per mole. When we remove a second electron, the ionization energy is much higher. And if you look at a table of ionization energies, and look at one that's organized by how many electrons we've removed, you'll find that for example, for magnesium, if we try to remove a third electron, the ionization energy doesn't just double, it increases much more significantly. And the reason for that is that we've now removed all the electrons that get us down to a noble gas configuration. So we're now trying to remove those valence electrons that are in the core shells. So as you go past the number of valence electrons that an atom is willing to give up, the ionization energy increases significantly. So ionization energy increases as we go from left to right, and it also increases from bottom to top. So our largest ionization energy would be in the top right, and our smallest would be in the bottom left. So you might notice, if you look at this in terms of which way things are increasing, this is actually exactly opposite of atomic radius. So the last term we're going to talk about in this chapter are electron affinities. So electron affinity is the energy change that occurs when 1 mole of electrons combines with 1 mole of atoms or ions. So there's a lot of words there. What it really boils down to is how strongly an atom pulls electrons toward itself. So electron affinity values become more negative as we move to the right. So if I draw my periodic table, and I'm just going to draw it as a box, just to represent what we're talking about. Electron affinity values become more negative as we go to the right, and they become more negative as we move up. Now this trend should remind you of something. This looks exactly like the ionization energy trend. So our most negative values would be in the top right, and our least negative values will be in the bottom left. Okay, so this is a table to kind of give you an idea of some of the electron affinity values. So there are some anomalies, there are some that don't quite go in the predicted trends, but for the most part we get more negative as we go to the right and more negative as we go up. Now, speaking of this table here, one thing I do want to point out to you. When you're doing some of these in your online homework system, there are some anomalies with all of the trends. So if you look in your textbook, you will be able to find tables of actual numbers there. Sometimes the online homework systems are very picky, and they will actually expect you to put it based on the order of the numbers in those tables. I do not emphasize those numbers because what's really more important at this point is that you understand the trends. But if you're trying to do an online homework system, you may need to look at those tables and see what the numbers are, because some of them are programmed based on what the actual numbers in the tables are. On a test, I would not expect you to know any of the values. I would only expect you to know the trends. But just a word of caution there if you're having trouble with a problem about a periodic trend on an online homework system. So, to summarize these and to show you why I do this in terms of which way things increase, if we go back to atomic radius, Atomic radius increases going left to right, and it increases going bottom to top. Sorry, top to bottom. So this one is atomic radius. So our largest is down here in the bottom left, and our smallest is up here in the top right. If we look at ionization energy and electron affinity, the trend is exactly the opposite. So our largest or our most negative is up here in the top right. And our smallest or our least negative is in the bottom left. So this is a trend for ionization energy, electron affinity, and we're going to find out in a later video that this is also the trend for electronegativity. So electronegativity is how strongly an element pulls electrons toward itself, how strongly it attracts electrons. So what you will notice is you have 4 trends to memorize once we get to electronegativity. But if you memorize the order in which these increase, you actually can boil this down to 2. Atomic radius increases right to left, and going down a column, ionization energy, electron affinity, and electronegativity all increase going from left to right and going up a column. So this summarizes all of the trends we're going to talk about, and we will get some practice putting elements in order of their trends in class. So I will see you in class.